Good afternoon, everybody. Welcome to the lecture on biomechanics of the knee joint. Now, in this lecture, we will be discussing about the structure, movements and degrees of freedom of the knee joint, followed by free body diagrams and static analysis. And the third topic is on calculations of joint reaction forces using solved problems. The knee joint is a major load bearing joint in the lower extremity. The knee is the largest joint and replicates a modified hinge joint. The knee joint is an essential joint in the skeletal system responsible for human locomotion and is vulnerable to injuries during sports activity. The knee joint consists of the following joints: the tibiofemoral joint, articulation between femur and tibia, between the medial and lateral condyles of the femur and the corresponding tibial condyles as shown in the figure. The patellofemoral joint, which is an articulation between the patella and the patellar surface of the femur, which is shown here in the X-ray image. Now, knee joint has 6 degrees of freedom. In the figure on the left, the translational degrees of freedom, the 3 translational degrees of freedom are shown along anterior posterior, medial lateral and superior inferior directions. The rotational degrees of freedom are the flexion extension, varus valgus rotation and axial rotation. So, this is indicated here also in the slide. Here we see the flexion extension, the rotational degrees of freedom, the varus valgus rotation. The anterior posterior translation is indicated here in this slide, in this figure, and the medial lateral translation is also indicated here, as well as the axial rotation about the vertical axis is shown in this figure. However, the predominant movement of the knee joint is flexion extension. The instantaneous center of rotation of the femur is of prime importance, because the location of this instantaneous center is very important for rigid body kinematics. The pathway of the instantaneous center of the femur throughout the range of knee flexion and extension is shown in this figure, the right side view, mediolateral view. In a normal knee, this pathway is semicircular. So, we see that with rotation of the femur, that is flexion or extension, the instantaneous center of rotation is rotating along the semicircular path. Now, how to find out this instantaneous center of rotation? We will take the help of the other figure that is presented on the right hand side of the slide. So, this is a left side view of the femur and the tibia. The points A and B, as you can see here, are points on the femur. The femur is rotated through a small angle and these points are displaced from A to A dash and B to B dash during the movement of the femur. The displacements A dash and B dash are shown in the figure. The perpendicular bisectors of these lines A dash and B dash intersect at the instantaneous center of rotation for the displacement shown. Now, clinically, a pathway of the instantaneous center for a joint can be determined by taking successive radiograph images of the joint in different positions, usually in small intervals of around say 10 degrees throughout, but it has to be taken throughout the range of motion in one plane, and thereafter we can apply such a method for locating the instantaneous center of rotation for each interval of rotation. Now, let us consider the tibiofemoral joint. We consider the flexion movement in the tibiofemoral joint of a normal knee. So, in the figure A as shown here, we will be discussing about the instantaneous center of rotation of the tibiofemoral joint. So, in a normal knee, a line is drawn from the instantaneous center of the tibiofemoral joint to the tibiofemoral contact point, that is located here. So, this line is designated by line P and is perpendicular with the line tangential to the tibial surface, that is line Q. The arrow indicates the direction of the displacement of the contact points. The line Q is tangential to the tibial surface, indicating that the femur glides on the tibial condyles during measured interval of motion. Now, in the figure B, we see pure sliding of the femur on the tibia during knee extension. However, there is no change in the contact point between the tibia and the femur. In the figure C, we observe pure rolling of the femur on the tibia during knee extension. There is actually change in the contact points of the femur and tibia while the femur rolls on the tibia. In the figure D, actual knee motion including sliding and rolling is shown. Now, let us consider the biomechanical function of the patella. On the left, we can see two figures A and B. The figure A shows the knee joint without a patella, and the figure B shows the knee joint with the patella. Now, you can observe that there is a difference in this distance. So, during extension, the moment arm of the quadricep tendon is considerably increased due to the presence of the patella. So, the mechanical advantages of the patella are: it aids in knee extension, producing anterior displacement of the quadricep tendon, hence increasing the moment arm of quadricep muscle force. It also allows wider distribution of compressive stress on the femur by increasing the area of contact between the patellar tendon and the femur. Let us look into more detail regarding the patellofemoral joint. So, on the left hand side we have a figure which represents the anatomy of the patellofemoral joint, and on the right we have a mathematical model of the same joint. In this mathematical model, there are some important anatomical angles, like the angle between the quadricep tendon and the femoral axis, indicated by psi. So, it is this angle between the femoral axis of the femoral tendon and the axis of the femur. The patellar tendon, the next angle is the patellar tendon and the tibial axis. So, this is the axis of the patellar tendon and this is the tibial axis. So, we need to find out beta. The third angle is rho, and that is defined as the angle between the patellar tendon and the patellar axis. So, axis of the patella and tendon of the patella. So, this angle. These anatomical angles corresponding to a flexion angle is necessary for calculations of forces in the knee joint. Now, let us consider the free body diagram of the patellofemoral joint. The patellofemoral joint is subject to compressive forces as indicated here, which is the resultant patellofemoral reaction force due to the patellar tendon force and the quadricep tendon force. So, the resultant force is a resultant of these two forces. The same thing is indicated here by the patellar tendon force PTF, quadricep tendon force as QTF. The resultant force passes through the instantaneous center of rotation of the patellofemoral joint. So, the resultant force is indicated here. There is another small force which is called TRF, tendofemoral reaction force, and that is between the quadricep tendon and trochlea, and the trochlea somewhere here as indicated in the figure. Now, the weight of the body is acting through the center of gravity and vertically downwards. The most important variable in the calculation of static forces is the distance d2, which is indicated here. The distance between the line of action of the body weight, the line of the center of gravity, and the patellofemoral instantaneous center, that is ICR. Changes in postures, either leaning forward or leaning backwards, will actually alter the distance d2, and it will significantly affect the calculations on static force transmission. Let us now enter into the second topic, the free body diagram of the knee joint. Now, static analysis may be used to determine the forces and moments acting on the knee joint. So, on the left we see a limb segment where the forces are indicated. So, a simplified free body technique as shown in the figure is used to analyze three coplanar forces in a two-dimensional system. The main forces in such a 2D system include the ground reaction force W, the patellar tendon force P, and the joint reaction force J. Now, when we consider the force P, individually the forces P, J and W, certain things are known and certain things are unknown. The known quantities are the direction and point of application of the force P. The magnitude is unknown. For force J, joint reaction force, both magnitude and direction is unknown, only the point of application of this joint reaction force is known in the form of instantaneous center of rotation. For force W, which is the ground reaction force due to the body weight, the direction, point of application and magnitude of the W force all are known. Now, since the limb segment is in equilibrium, the lines of action of all the three forces intersect at one point. They have to intersect at one point since the limb segment is in equilibrium. So, this system of force, from this system of force, the line of action of the force J is found out by connecting the point of application of this force J and the intersection point I. This intersection point I is found out by extending the lines of action of forces P and W as indicated in the figure. Since the force system is coplanar and in static equilibrium, the joint reaction force J can be found out using the force triangle as indicated in the figure. In the force triangle method, the length of each side indicates the magnitude of the forces. The moments acting around the center of rotation of the joint during stair climbing can be easily found out from the free body diagram shown here. The magnitude of the patellar tendon force P can be obtained by considering equilibrium of moment about the joint center. So, we have the force W acting through a lever arm A. So, that creates one moment along about the joint center here. There is another force P which is acting through the lever arm B, that is creating a moment in the opposite direction. So, the two opposing moments WA and PB can be equated through the moment equilibrium equation, and we can find the P force in terms of the dimensions AB and the weight of the subject W. Let us now move into the calculation of joint reaction forces. The figure on the right shows the knee at a static position. So, we need to estimate the quadricep muscle force necessary to maintain the knee flexion at 15 degrees. The direction of the muscle pull PT is at 60 degrees with horizontal, and the body weight is 60 kg. Considering the moment around the joint center and moment equilibrium, we can actually write down an equation connecting the patellar tendon force and the weight of the or body weight W. Now, this force PT is acting at a distance dm from the joint center, whereas this is indicated by dm, whereas the weight, the body weight is acting through the lever arm xw as indicated here. So, xw is the distance between the joint center and the line of action of the body weight. Now, if we consider the given data of 50 and 60 millimeter for dm and xw respectively, we can substitute these values and find out the patellar tendon force of 72 kg force based on the data given for this problem. In the second problem, we consider a person in a sitting posture. This subject is actually wearing a boot of weight WB. So, the figure illustrates forces acting on the lower leg while flexing in a sitting position. So, we need to find out for this instant the tibiofemoral joint contact force or joint reaction force and the tensile force in the quadricep muscle. So, the weight of the boot is indicated by WB. The weight of the lower leg is indicated by WL. The tibiofemoral contact force Fj is indicated in the figure, and the tensile force in the quadriceps muscle is indicated by Fm. The center of gravity of the leg is located at B, and that of the center of gravity of the boot is at C. The line of action of the muscle force Fm is oriented at an angle theta with the long axis of the leg as shown in the figure. Here is the long axis. Now, this long axis in turn is oriented at an angle beta with the horizontal direction. The simple mechanical model of the problem can be represented as shown in the free body diagram here, where we have the muscle force, we have the joint reaction force, the weight of the lower limb, the weight of the boot, and the angles theta, beta, and the dimensions A, B, C. So, considering the moment about the joint center O and moment equilibrium, we can write down the equations of the moments. So, the first term is the moment of the muscle force, the second term is the moment of the limb, and the third term is the moment created by the boot, the weight of the boot. So, these can be related through the moment equilibrium equation, from which we can actually express the muscle force in terms of the related variables as shown in equation 1 or I, equation 1. Now, assuming the joint reaction force Fj makes an angle alpha with the horizontal, we can consider the force equilibrium along x axis, that is summation of the forces resolved along the x axis, and we can write down the equation as shown in this figure. So, Fj can be related to Fm according to the equation number 2. The force Fj makes an angle alpha with the horizontal, and we can also consider the vertical component along the y direction. We can resolve the forces along the y direction. So, we can write down the equations relating Fj, the vertical components of Fj, Fm, and the weight of the limb and the weight of the boot. So, we finally write down the equation 3 connecting the joint reaction force and the muscle force in terms of limb weight and the weight of the boot. Now, from equation 2 and 3 that we had developed earlier, we can actually, combining the two equations, we can actually find the expression for tan alpha, which is the angle at which the joint reaction force is acting. The angle alpha is the angle at which the joint reaction force is acting, indicated in this figure. Assuming the geometric parameters in terms of height h for the geometric parameters and weight w, there is A, B, C, the dimensions in terms of height and the weight of the limb and the weight of the boot, weight of the limb as 0.085 W and weight of the boot is 0.065 W, assuming these two, and the angle theta as 18 degrees and beta as 47 degrees. We can substitute this in the equation and find out the quadricep muscle forces, the tan alpha, the inclination angle of the joint reaction force, and the magnitude of the joint reaction force. So, these three important solutions of the problem can be obtained in form of the quadricep muscle force, the joint reaction force, and the angle alpha, the inclination of the joint reaction force. I would now like to present the variation of knee joint reaction force, the tibiofemoral reaction force during normal walking. So, this is On the x-axis we have the walking cycle, and on the y-axis we have the tibiofemoral joint reaction force. This is the resultant tibiofemoral joint reaction force. So, here we see that the peak resultant joint reaction forces during walking vary between 2 times body weight to 3 times body weight. So, it can vary between 2 times body weight to 3 times body weight. The first peak normally occurs at 18% of the gait cycle. The second peak normally occurs at 57% of the gait cycle. The magnitude of the two peaks is approximately similar and has been reported to be around 2 times body weight, 200% body weight for the first resultant, and around 240% of body weight or 2.4 times body weight for the second resultant peak. Now, in this table, the peak joint reaction force, the tibiofemoral joint reaction force during different activities have been listed, wherein we can get the maximum knee joint reaction force. So, it can be observed that the range of peak values of knee joint reaction force varies considerably with the activity. So, during level walking, we can see that it can vary from 2.6 to about 3.4. During downhill, it goes to about 7 to 8 times body weight. During uphill, it goes to a peak of 3.7 times body weight. During descending stairs, it varies around 3 times body weight. During jogging, it may vary from 3.1 times body weight. It can also go to 4.5 times the body weight. The patellofemoral joint reaction force is listed here for different types of activity. As you can see, it is the reaction force between the patella and the femur joint. During walking and cycling, this force is quite less because these activities does not involve too much of flexion. That is the reason the patellofemoral joint reaction force is still low as compared to the other activities like stair ascent, stair descent. It abnormally rises to from 3.3 times body weight to 5 times body weight. In jogging, the patellofemoral joint reaction force is predominantly high, 7 times body weight. Normal squatting is 7 times body weight, and deep squatting, which is actually all the squattings are actually high flexions movements. So, in these squatting mode, the patellofemoral joint reaction force can rise up to 20 times the body weight. Let us now come to the conclusions of this lecture on knee joint biomechanics. The knee joint reaction force depends on the gravitational force due to body weight, the lever arm of the gravitational force, the force exerted by the quadriceps muscle and the patellar tendon, the lever arms of the quadriceps muscle and also the lever arm of the patellar tendon. The peak tibiofemoral and patellofemoral joint reaction forces are largely influenced by the activities performed by a subject. The list of reference is indicated here. It's a long list of 3 slides. You can refer to these references, and thank you for listening.